process capability and create certain measures for it. And we had talked about defect probability, and defect probability was determined by capability index. Capability index, when capability index is higher, the probability of creating defects is lower. So that is something that you need to remember. Now, we also we also had discussed parts per million, which was another measure to measure how accurate our process is. Oh, people are leaving the session. I hope they will rejoin. So we got to the point where we understood that parts per million, it's the number of defective parts that could be produced as far as the process is concerned. And we established that in 6 sigma process, the process where we had 6 sigma on each side of the normal distribution curve, the parts per million doesn't even make sense, because in this 6 sigma process, the accuracy is so good that we have 2 parts, defective parts per billion. Then we were analyzing how to build the target variation, and we came to the conclusion that if all of a sudden we were given different assignment and we could build the utilizing the formula of capability index, which looked like this. Just let's go one back. You see? So this capability index was USL minus LSL divided by 6 sigma hat. So utilizing this formula, we could, if we were given capability index and target to minimize the number of errors per million, we could calculate the what in this particular case our sigma has to be. So now that we know how to establish process of great accuracy, just like Suter people did, we can go back and we can look how to keep this process conforming to the accuracy that we established. Okay? In order to do that, we have to come up with a control charts. And the control chart in this case is called X bar. It is X bar because it is X bar stands for X with a little line over it. And X bar is the average of all of our metrics that we create by looking at results of our production. Excuse me. Wow. Anyway. So this is what helps us to identify the limits of our production. The way we define it, before we go there, I'll show you how it's done. I hope now you can see the screen, which is the snapshot of the actual textbook. And you can see the slide, which says figure 9.7. And this is the process parameter, where on the X axis, we will establish how many times we will run those samples. And here we will measure the size of those samples, and in this particular case, averages. In order to better understand it, here's what engineers in Suter did. They, for a period of 25 days,
Excuse me, Professor?
Yes.
We can now see the book. Right now we're looking at the PowerPoint.
You looking at PowerPoint, huh?
Yeah.
Let's share. Hold on, let me try it again. You should be able to see it. Okay. And thank you for letting me know. Okay. How about now?
Not yet.
I think you have to share your screen.
What's that?
I think you have to share your screen with us.
I am.
Oh, we can see it.
You can or cannot?
Cannot.
Okay, let me go back. I don't know why it doesn't work. Because I was sharing my screen with you. Okay, let's see. Try it again. Share. How about now?
Still, just the PowerPoint.
Okay. Then we'll have to figure it out at some point. But let's see. I'll try to do something different and unconventional. So now you see PowerPoint, right?
Yeah.
What about? Can you see the blank screen?
Yes.
Huh. You can't see the blank screen. So if I wanted to do this, my chart would look like this. I know it's not greatest way to do it. So what I would do is that I would take here, I would make a line, which we will establish what this line means, and this would be called X bar. Here we would make an upper limit, and I'm getting better at this. Well, I don't want to write letters, but this is going to be UCL, upper control limit. And this here would be LCL, LCL, and this is lower control limit. So the way the engineers done it on in the extruder plant. Every day they started doing it on day one. That's one. And they had, that's one, and they did it every day for 25 days. And they're controlling the size of that support by measuring it. And what they do, they take, every day they take five parts out of production. So in other words, they make 5 measurements. It's X1, X2, and it becomes X5. I'm not going to write them all. So after they've done that, they calculate the average of those metrics. And the average they put on this graph. Okay? And it would be something like the first day it would be here. The next day it could be here. And so on and so forth. And it's like this. Now, they need to know in order to figure it out what this medium line is, X bar, is that when they've created a table, which again, if I wish I could share it with you, the table in your books, oh, you know what? How about this? Can you see the table now where my picture was?
Yes.
Okay, cool. So this is the table which has 5 columns and 25 rows. And we're going to just talk about it. Now I have a homework assignment to figure out why I cannot share my screen with you. But did somebody say something?
Professor, is it table 9.1?
It is a table 9.2.
Thank
Yeah.
you.
It is helpful if you have book next to you, then it will help you until I can figure out how to share my screen. So now this is table 9.2, and it has 25 rows and it has 5 columns of x's. So when I'm taking x at the end of each row, I can calculate. Thank you, Uzi, Hallie. So at the end of the each row, you have an average, and the average of those is x bar, and that's what's put on this graph. Now, the middle line is the average of averages. So this is the number which is at the very bottom of the table on the right-hand side. Oh, somebody was able to fix something. I wish I could fix mine to show you the book. But now, in order to do that x double bar, this is x double bar, you have to calculate average of averages. In other words, it's the average of all 25 numbers by 5 numbers, whatever that is. Once you've calculated, that becomes your middle line, and that's what's on page 2. Now, what we also need to calculate in this case, let me see what the next slide is. Next slide. Oops. Shared slide. Oh, yeah. That's not perfect yet. I don't know how to get back to the slide that I just showed you painlessly. So this is the slide where it talks about x bar bar, which is the middle line. This is called x bar chart. We talked about that. The smallest value is LCL and the largest value is UCL. And this is where we have to make sure that the part size does not go above the upper control limit and lower than lower control limit. If it goes either one of those, then the part is considered to be defective, and we need to understand why it happened, and we need to eliminate the cause of that mistake. So, but in order to build and figure out what UCL and LCL are, we know how to calculate X double bar. X double bar, you've taken average of all averages. Now we need to calculate X double bar, and X double bar, UCL and LCL, we need to have a couple more parameters. So first one, we have to figure out estimated standard deviation of all parts. When you get to your test, midterm exam, this value will be given to you. I will not have to have you figure it out. So, and this value basically in real life is figured out. Well, there are many ways, but one of the ways that is suggested to you is to take Excel spreadsheet formula, which is stdev.s, and enter into that formula all 25 multiplied by 5 numbers. After you've entered all of that, it will generate a specific number for our specific example. And this number is given to you in your books. I don't want to give it to you now because it doesn't make sense anyway. It's 0.01784, whatever. But this number is needed because it is nominator for the other parameter we have to calculate. And this other parameter is called estimated standard deviation of X bar. And when we get to the formulas, you will see how it is specified. So in that case, estimated standard deviation of X bar is standard deviation of all parts divided by square root of n, Nancy, where n is the number of samples you've made, not the number of days you were checking it. In other words, it's not the number of rows, it's the number of columns in your table. Everybody understands it. It is a key because a lot of people make this mistake. N is the number of samples you've taken. So again, we'll go of the problem but hopefully soon by the end of this conversation, and you will see how it is done and how it is calculated. But in our case, in our specific example, the n equal to 5. So the denominator of estimated standard deviation of X bar is square root of 5. And after we've calculated that, then we can get to the formula that looks like this. So UCL is defined as X double bar, and as you all recall that this is a average of averages, and then plus 3 multiplied the estimated standard deviation of X bar, and LCL is the same but minus 3 estimated standard deviations of X bar. The question is, why is it 3? And the 3 is the same 3 that we've taken when we were working with the capability index, if you recall. In the capability index, we had a what we called at the time, we called it 3 sigma process. And that is very similar to that. Because in this particular case, with 3 sigma process, you can say that if your all of your measured samples fall in the middle of those 2 UCL and LCL lines, then with probability of 99.7, you do not have a problem of defect. Because if it occurs that there is a defect, then the process is showing that your process now has the attributable cause in inputs or environmental causes which cause this defect. So that's why it is very important to understand that this is how we maintain conformity with our accuracy of the process and how we analyze it. So it is very important to understand also that there are other things that we are looking for. There are, for example, unusual situations. Let's say all of a sudden several samples, one after another, appear above the medium line. That would also kind of raise our attention because the probability of having to have 8 samples all appearing above the line or below the line is very, very insignificant. And that would indicate the process is running kind of wrong. Because again, if probability of each of the samples being either above the line or below the line is 0.5. You have just like tossing the coin. People who are leaving the session, are you leaving the session because connection is bad, or you're losing connection? Because I have kind of indication that some people coming and going once in a while. Okay. Has anybody raised their hand so far? No. Okay. All right. Nathlin, are you doing something with your raised hand and lower hand? Because for some reason it pops in and out all the time. Okay, good. So anybody? Oh, okay. Thank you. What? I couldn't. Let me see what you said. Overused. Are you saying that internet connection is bad today? I see. Is it? It might be because of the weather. But you know, it's pretty consistent. There are 35 of you, which is impressive. I'm very happy about this. You get the credit, guys, because it isn't easy, I know, for everybody. Okay, so now let's go back to this stuff. So probability of sample being above the line or below the line is 0.5. So in order for something happen 8 times in a row, it would be probability of that would be 0.5 to the 8th degree, which is 0.004, which is incredibly small and unusual. That's why in this particular case, you would know that there is a reason for concern and you should go and analyze and figure out what the issue is. Now, why is it important? Because this is how, in reality, in real life, people make sure that their processes are running pretty accurately. As an example, I can give you like it's a kind of apropos story, because recently some people did go to spring break, and you will have a spring break in April. I hope you're not going to repeat the mistake of other people and go and get exposed to coronavirus. But in Florida, in Miami Beach, they were testing the emergency service, and they were figuring out how, because the standard, I don't know if many of you know it, in the big cities, this government federal standard to get to the on the call of emergency in the cities, it must be below 15 minutes, which is very high. In New York City, it's about 6 minutes in reality. And the same in Miami, I think it's about 6.7. If you are in the rural area, there it is up to 30 minutes. So if any one of you is planning to have a heart attack at any point of time, it's better to be in a big city than to be in a rural area. Because in the rural area, most likely, by the time the emergency does get to you, this person will be dead. So, but none of us has to worry about it at this point in time. You're still young, and I'm trying to stay healthy. So anyway, at least until this semester ends, I want you guys finish it successfully. So that's why in Miami they were running this test. And the way they were doing it for like 10, 15 days. And they were taking samples 4 times a day, in the morning, in the early afternoon, late afternoon, and at night. And for all 10 days, everything was running perfectly fine. the samples were falling between a lower control limit and upper control limit. But then on 11th day, all of a sudden, it jumped out above control limit. And they started investigating what had happened. And they started looking at the reason, and specifically in samples that were taken on the 11th day. And what was happening is that this was the first day of spring break. And a lot of calls were made from the beach. And it takes a lot longer to get to the beach than to any point in the city on average. And that's how they discovered that when people get on a spring break, they go to the beach, then they drink, smoke, or whatever else. And there are a lot of calls, higher volume going there. And that was interesting because since then, every time when you go to the beach, I'm sure you're seeing the emergency vehicle standing right there and then, and the police probably, because they do not want to have a long time to get to the place of emergency. So that was how it was discovered. Well, and that's basically important to know. Now, let's talk about a couple other things. How can we now understand the process? And I will go, hopefully we'll have enough time. I will go over the example of a problem, which would be a similar problem to the one you will have in the midterm exam, which I'm planning to give you. So, how do you usually investigate the assignable cause? When you see this defect and when you collected this chart and you identified that you're all of a sudden one of your samples or couple getting above or below UCL and LCL, you start a real careful analysis. And one of the tools that you use in this analysis to figure out the root cause of the problem is called Fishbone diagram. It was invented by Ishikawa, a Japanese scientist who was operations maven. And what he created is diagram that you can see at the bottom of the slide. Well, everybody understands why it is called fishbone diagram, because when you make that diagram, it starts looking like a skeleton of a fish. And the way it's created is what you do, you have a major, did somebody have a question? Let me see. No. You have the thing that the defect that you have identified. In this particular case, the defect is steer support height deviates from specification. In other words, it's either above control line or below control line. So in this case, you draw the horizontal line with the arrow showing that defect, and then diagonally to that horizontal line, you create separate groups. And the groups are usually machines, specifications or information, people, materials. That's in manufacturing. In service, the names of those groups are slightly different. And then you start horizontally putting different reasons why something can go wrong. And I'm not going to read all these small details on this chart because you will all see that there are a couple of good examples in your book when you look at your book. But the point is that it's an excellent, even though it's quite simple, but it's an excellent tool to use for brainstorming sessions when you as a group sitting and figuring out why all of a sudden the parameter that behaved historically well, all of a sudden started behaving not well. So like I said, this is called fishbone diagram. The other tool that people use, especially in Japan, to identify cause-effect relationship is the method which is called 5 whys. Has anybody heard that method? So 5 whys method is when you ask 5 times what happened. And hopefully by the time you ask this question 5th time, you will know the actual reason. And the best thing in this case, I give my students the example about student who comes to the class late. And when the student comes into the class late, the student gets asked, why are you late? That's the first question. And the student says, I had to go and get my coffee in the coffee shop. So then you say, how come you go so far away to get your coffee? Why did it take you so long? And the student says, because the coffee in where I buy it is much better than in the coffee shop in Baruch downstairs. So then you continue asking this question and you say, why is the coffee cheaper and better quality long distance coffee place than it is in the building? Obviously, the answer here is because administration of Baruch gave the rights to an outsourcer to provide coffee, and this outsourcer has a monopoly. And when you ask them why they don't care about the quality and the price, is because they think that people do not have anywhere to go. So as the result of me asking this question 5 times, I'm coming now to the conclusion that the lateness of the student is attributable to university. It's not that student is at fault. It's university that is at fault because they gave monopoly of coffee making to a company that is not doing a good job. So now every time when you ask why you're late for the class, you can try to sell this idea. Obviously, you will not be successful selling it to me because I told you this story. Okay? So now, in real life, you may have multiple causes to your problem. And when that happens, with multiple causes to the problem, you need another tool that will help you to figure out which of the causes are more important and on which of the causes you have to focus to fix the problem. And in this case, there was a scientist in the United States who propagated the what we now call Pareto principle. And scientist's name was J.M. Juran. And what he did, he studied Toyota production, and he created Pareto principle and Pareto diagram. Pareto, you remember we talked about early in the semester about Pareto domination. That is the same Pareto. It's Italian manufacturing guru. So what this diagram does, in Pareto diagram, what you do is that you calculate how many occurrences of specific defect. Well, first, Pareto principle. That is something important because there is a question similar to that on your midterm test. And the question is, what is Pareto principle about? And Pareto principle is about the fact that 80% of the problems are caused, or defects, are caused by 20% of inputs or environmental causes. And that was very important to discover because managers historically used to waste a lot of time on fixing problems that were not important because they did not have that magnificent tool, which is called Pareto diagram. Now, on this slide, you can see.
Could you please repeat that? What
Repeat.
that principle is? Could you please repeat that?
Sure.
Thank you.
Pareto principle is that 80% of the problems are caused by 20% of wrong causes, bad causes. Yes, you're right, Andrew. It is found everywhere because 80-20 rule is working almost everywhere. But for the first time, it was actually specified, surprisingly, by Juran. And it was done because that was widely used by people in analysis of issues. And what they did, they calculated, they've built those Pareto diagrams. Here you have a little example. Again, I'll just quickly show you what it does. What it does here, it is listing. I actually like the book example a little better. Here on the slide, it lists the root causes of the problem of bad delivery, broken delivery of Xooter to end customer. So it lists out the frequency. For example, broken during reloading, 33 occurrences. Broken at customer property, 22 occurrences. Broken at the truck, 9 occurrences. And so on and so forth. And at the end, fraud by the customer, 1 occurrence. So traditionally, people who didn't know Pareto method, they would start investigating fraud issue, trying to blame everything on the customer. Now, in our case with Pareto diagram, we have a better situation because now what we can count the number of frequency of occurrences. Total problems are 87, total root causes. Calculate the percentage of each of them. So when you calculate the percentage of each of them, you put it on a Pareto figure, which is figure 912, as a bar. So in other words, the first one is 33, frequency 38%, which is like 40 here. It's a little bit not accurate. Then the next one is 22 occurrences, and the percentage of that is smaller. It is something that is a difference between 63 and 38 because this shows cumulative percentage. And that is the second bar on your graph. Also, why these cumulative percentages are shown, it is the blue curve that is shown at the top that goes from 40% to 100%. This curve basically is identifying to you cumulatively percentages of those bad root causes that cause the problem. Now, if you look at the graph and you take the horizontal line at 80% of the graph, you will see that first 3 causes generate 80% of the problems. Can you see that? I hope so.
Yes.
It is clear by looking at the graph. And that's why this little graph is very, very helpful and very good for you. So this is Pareto diagram, Pareto or Ishikawa, or a principle, I'm sorry, Pareto diagram, and the principle, Pareto 80-20 principle. So that's something important. By the way, it is important for people who will choose the job of Six Sigma, Lean Six Sigma experts, analysts, because those are the terms that widely and tools that are widely used in there. The Fishbone diagram, the Pareto diagram, those things you need to know for that. Okay, now, what do we do to make, we cannot always control variability. In many cases, we need to create a process so robust that even if root causes, the inputs become defective or there are severe environmental defects, you still are able to create a output which is not defective. And that is how do you make your process more robust. And you make your process more robust by eliminating root causes of the problem or making it withstand those problems. And there are three ways to do that. One is over engineering, and this is where you make the process so strong and so robust that it is not going to break if something happens along the process. So, for example, in the case of our mass Estonia, if you recall, engineers, when they designed that ferry, they could have taken into consideration that people can make mistakes balancing the load. They could have made this ship much broader and much more stable to withstand the stormy weather. And if they've done all of that over engineering, the catastrophe might have been avoided. So that's something that is called over engineering. Foolproofing. Foolproofing is simpler. It's something that the best example for it is the one that we learned when we talked about the poor medical intern who made a mistake and injected the medicine into a baby instead of orally into IV. So what the hospital did at that time, they redesigned the syringe and they made the syringe in such a way that it's foolproof. In other words, you can only use it for either oral introduction of medicine or for IV. So in this particular case, it was successful because not only they implemented something foolproofing the process that mistake cannot be made, but it's also educational for the student because now if they even tried it, they couldn't make mistake. So another simple example, you all travel or will travel at some point in time again. You go to the airport and when you check in on the plane, there is this little gadget, a frame of tubes where you are asked to put your hand carried luggage in. And if it fits in, you take it on board. If it doesn't fit in, you have to check it in. That's a typical foolproofing example because here you in one shot you are able to, without specific measurements and anything else, you have to identify if this piece of luggage will fit ultimately into overhead compartment or not. And finally, the third method is early warning signs. And the early warning signs are also simple. If in case you had the boat and on the boat there would be a problem, that would generate some kind of a signal that your load is not distributed properly. So that's another example how this could have been avoided. So those are the three ways to make process more robust. Okay. Now, this particular part is section is talking about defects with binary outcomes. We're not going to spend too much time on it. I will just quickly describe to you what it is. It's when you cannot measure every part of your process or service, duration, let's say, or length of the part or height of the part. All you really can able to establish is the process good or bad? In other words, did it generate a defect or didn't generate a defect? A simple example of that is when you managing a delivery service, let's say post office, and you have a metric that post office operates is that only 3% of parcels can be delivered in error. Or like in case of Federal Express, we talked about before that only 1 0.1% can be delivered in error. So Federal Express is more accurate. Now, in this case, what you say is that you need to, in order to figure out if this process is running reliably or not, you have to make another way to say take samples, but in this case, you must take a lot more samples than 10. In this case, because if the probability of error is only 1%, taking 10 samples is not going to even show that error. So usually when you run the binary defect metric, you have to take 50 to 200 samples in order to pick up the one that is bad. So that's, please do not leave session before it's time. We still have time. Anyway, so in this case, what we do, we create p-charts, and p-charts are very similar. And I'm only showing it to you so that in the future you will know what they are. But it's not going to be present on your test. It's something which is very, very similar to X bar chart, but here you calculate the probability of defects, and you count how many defective deliveries were made, and you make it on the sample basis. And then there is the same way to build the P chart, which formula is much simpler in this case, and it is the estimated standard deviation calculated, where P bar is the the sample average of defects probabilities, and 1 minus P is non-defects, and divided by sample size again, and sample size in this case has to be between 50 and 200, and UCL and LCL also calculated similarly to X bar. Okay, so in this case, that's basically it for that particular thing. And there are binary trees that are, if people are actually interested in it, you can calculate them, and you can logically think how to figure out the probability of errors in those processes. Okay, this is example how problem is solved for check understanding, but I think that more importantly in your books there is a check understanding which is this one is, I think, some 9.8 check understanding, but you should all look at check understanding 9.5, and 9.5 is in your books, and this is something that talks about 50 days process engineers are measuring weight of component after coating it with a special paint. Unfortunately, I do not have a slide for it. I used to have it in the prior deck, but for some reason they lost it. So I beg you, go through this example. Make sure that you read it and understand how to do it, and pay attention to the fact, even though they ran the test for 50 days and were weighing the parts during those 50 days, the sample size was 10. And 10 is the number that goes on in the square root when you calculate estimated standard deviation of X bar. I do not remember what page it is in your books, but do look at that check understanding, because problem very, very similar to this. Thank you, Hailey. 267, very good. I actually left my book in college and I didn't want to go back there. So 267, that's good. So do go through this problem, and this is very good as a sample of what you will see as a problem on the exam. Okay. Now, the last thing I want to mention to you regarding this chapter is there is only one term that for some reason this book doesn't cover, and this term is called DMAIC methodology. DMAIC stands in as define, M as measure, A as analyze, I as improve, and C as control. I can repeat it. DMAIC methodology is used in Six Sigma analysis when you make some processes of production Six Sigma compliant, and it stands for define, measure, analyze, improve, and control. Okay? Anybody who didn't get it, raise your hand. I will repeat it again. But okay, everybody lowered their hand. Okay, let me see. Anybody is raising hand? No, I don't see anybody with a raised hand. Okay, good. Are you raising your hand or lowering your hand? Okay, I have 5 people with raised hands, so I repeat. DMAIC methodology. It is used in Six Sigma analysis, and DMAIC methodology stands for define, measure, analyze, improve, and control. So it's the process. It pretty much defines, it's a different expression of what we studied in this chapter. In other words, at first, I can type it for you. Sure. Sure, I can type it for you. I can write it for you. It's DMAIC. Right? Can you see it? Good. Anyway, so that's what it is. So when you go for an interview, if you want to become an analyst, you will know what that is. And again, it's just another tool to be used. You show that you first will define what the problem is. Why is your hamburger is coming out with weight which is wrong on a certain time, and then you will measure it, and we will identify how wrong it is. You will analyze the root causes of the problem, and then you will come up with an improvement procedure of the process, and then you will start controlling your process. And this will be repeated many times in life. And that's completing our discussion on statistical methods and how to control your processes. Okay? Now, that's something that I wanted to do for now. What I want to tell you, okay, Professor, how would you describe the inefficient? Oops, I cannot see. That was so fast. Let me see it again. Just a second. It was very fast. And I didn't catch it. Why can't I see it? Let's see. Define, measure, analyze, improve, control, right? But somebody just asked the question and I couldn't read it for some reason. It appeared and disappeared too quickly. Can you voice your question by unmuting your microphone?
Professor, it's me. So I had a question. I keep hearing this on the news. How would you describe the ineffectiveness of the Labor Department in aiding New Yorkers at this moment? And how do you think it could be improved in these times?
Well, I tell you what, unfortunately, fortunately for me, I live in Jersey. Unfortunately for you, people who live in New York, your governor, excellent job. Governor Cuomo is very good, and he's demonstrating his leadership ability. Your mayor, on the other hand, is not. And That's why you cannot improve the efficiency overnight, because he let it go for too long and he is not productive. That's my personal opinion. You don't have to follow what I said. But anyway, I don't want to lose you all before we go. What I want you all to do after we finish the session, I want you all to, who did not say anything on the chat, say something, hi or bye or whatever. This way I will know that you who was there, and you will be checked in. Now, the other thing I wanted to let you know that we will have our class next Wednesday, the same way as we did today. Hopefully I'll have better voice by that time and will be more successful as far as sharing the screen. I also want you to know that we will have a test, midterm test, and midterm test will take place most likely next Monday. And the way it will take place is by me publishing it on the website, and I will send an announcement. But before you all go, I want you all know that I will keep my office hours between 4 and 5 every Monday and Wednesday. And we all, anybody who wants to talk to me, please raise the question to me in email, and I will reply to you when we can have a conference call, or later on I will probably even have video calls with people who want to be consulted. Okay? Now, the chapters that are covered in test are the chapters that we covered. 1, 2, 3, 4, 16, 8, and 9. 8, as you recall. Yes, there is a group project. 1, 2, 3, 4, 16, 8, and 9. Very good. The group project was defined and described on course material on the Blackboard.
Professor, I have
Yeah.
a question about the group project. So one of the parts is to have a oral presentation. So as you know, that's gonna be a little hard knowing the system. It's gonna be tricky for us to like
No, it's not.
facilitate.
By the time we get there, don't forget it will be at the end of the semester. And by the time we get there, we will figure out the best way to do it. To the point that one of the possibilities will be that the group will choose whatever the tool they want, and they will record the presentation, and they will submit this presentation to the what you call it, to Blackboard, and we will all see it. Okay? So we will talk about whole thing about projects. Read Blackboard project description, project guide before you start bombarding me with questions. The main question is how to select the teams. And this is what I want to tell you now before we leave. Selection of the team, apparently everybody has a problem because very few of you know who is who. So now what you can do is that you can, if you tell me, send me again, I already got the messages from a few of you, send me messages stating that you need help, or saying that you have a group of 2 or 3 people. And this way I will not break you into other groups. So I will, yes, and you already sent the message, I know. So I will break you all up in groups, and I will suggest to you groups, and you will have to work together by utilizing technology. Okay? So do not worry about it. It's easy. And actually, I think for the first time, it will be very easy because you all will be obligated to communicate not face to face, but on other media. which is excellent because in business today, a lot of things, a lot of projects are run online.
Professor, what if I already have a group formed, like we have
If
like a good amount of people,
Guatemala, that's good. I like that.
and also well, I got one professor that we have a presentation, and what he did was he made us record the audio in PowerPoint. So like every slide is gonna tell you what we have to say about that slide. So I
Okay.
think that could be a good option of how we could
Yeah,
do it.
but whatever you choose, any method of delivery, but make sure that you follow instructions that I published on Blackboard. Okay?
Okay, no
Sounds
problem.
good.
All right. Good. That was reasonably successful, and I appreciate your patience and consideration, and I appreciate that you all showed up. So I will feel better. I don't know what happened to me.